So now we're going to look at the case of what we do when we do not know what the population standard deviation is. In the previous two examples, we used a z-interval because we knew what the population standard deviation was. So now if we don't know what the population standard deviation is, that's where the student t-distribution comes in. And a lot of times it's just called the t-distribution, but it's called officially the student's t-distribution. Now, the student t-distribution looks really similar to the normal distribution, but it has thicker tails because it accounts for more variability. And that is because we don't know what the population standard deviation is, so we have to account for that extra variability. Now, as the sample size increases, the t-distribution becomes closer and closer and closer to a normal distribution. Now, the shape of the t-distribution depends highly on what's called the degrees of freedom. And the degrees of freedom, we abbreviate it DF for degrees of freedom, that's just one less than the sample size. So if the sample size was 20, the degrees of freedom would be 19. So in blue, you can see the standard normal curve. And then the green and the red curves are t-distributions with different degrees of freedom. And the shape changes as the sample size changes. Let's look at some of the characteristics down here. For the key points, it says the t-distribution has thicker tails than the normal distribution. Oh, that's just restating what I just said. That's extra. As the degrees of freedom increase, the t-distribution becomes more similar to the normal distribution. We use the degrees of freedom to compensate for the unknown variability due to not knowing what the population standard deviation is. The degrees of freedom affect the shape of the t-distribution and the critical values used in the confidence intervals. And the formula for a one-sample t-interval for the degrees of freedom is n-1. So these are all the key points of information. Something that I didn't put down here in the key points, but I'll add, when we're finding a t-interval, if we need to find the t-critical value, we want to use the t-distribution, not the normal distribution. But the process on how we do that on GeoGebra is the same. So instead of having z-scores, we're going to have t-scores because we're looking at a different distribution. We're looking at the t-distribution. But what it represents and how we find it on GeoGebra remains the same. It's just coming from a different distribution. Let's look at example 3. A random sample of 16 Americans yielded the following data on the number of pounds of beef consumed per year. Use a 95% confidence interval to estimate the average number of pounds of beef consumed each year in the United States. So we need to come up with a 95% confidence interval for a mean. Now, because we are not told in this question what the population standard deviation is, and we're told that these values here is from a sample, not from the population, so we can't calculate it directly. So let's find our information so we can hop on over to GeoGebra and enter the information to find our confidence interval. So we need to know what our sample size is, and this is telling us that it's 16. Now, sometimes it's not given to us. If we have the data, we would just need to count the data values to see how many there are. It's nice when it's given to us in the problem, though, so we don't have to count. Okay, we need to know what the sample mean is, and we can get that from GeoGebra. We know our confidence level is 95%, so I'm going to put that in there. We're also going to need to know what our sample standard deviation is. That's our S. And if we want to do this by hand, we're going to need to know the T critical. I'll show you how to get that on GeoGebra as well. Okay, so now that we're in GeoGebra, enter your values from the question, and then we can use that to calculate our sample mean and our sample standard deviation. So pause the video for a moment and enter your data. Okay, now that we have the data in there, I'm going to highlight from 1 to 16. I'm going to come over and choose one variable stacks. And then I'm going to choose the sigma x so we can see our statistics. And we get that our mean is 118.4375. We get that our S, our sample standard deviation, is 5.6565. So that's what we're going to use to put in to calculate our confidence interval. Now, since we're doing a T interval now, not a Z interval, because we don't know what the population standard deviation is, I'm going to make sure that I choose T estimate now. And then I enter all the values like I normally would. So this is a 95% confidence level. I'm going to put in the mean. Put in all the decimal values and wait to round at the end so that the intermediate steps of rounding doesn't throw your final answer off. So make sure that you enter in all the values that you're given. Okay, for S, our sample standard deviation, that's 5.6565. I got that from right here. My sample size is 16. And now we have our T interval down here. Our lower limit is 115.4234, and the upper limit is 121.4516. And here's the error. I'm going to copy that down so that we can check this by hand. Here's the error. And we need to find the T-score to calculate the error first. So let's hop over to the distribution tab and let me show you how you can find your T-score. So instead of using the normal curve for the Z interval, we're going to switch to the student T distribution for a T interval. Right here where it says DF, remember the degrees of freedom is one less than the sample size. The sample size is 16, so the degrees of freedom is 15. So I'm going to put 15 in there. Now, to find our T-score, it's exactly the same process that we went through before. If we have a 95% confidence interval, that means 95% is shaded in the middle. So that means there's 5% left over. And when we split that between the two wings, we get 2.5% in each wing. So I'm going to look at the left wing first. I'm going to put in 0.025 for 2.5%. And we get that our T-score is negative 2.1314. Now, if I check it on the right side, I should get the same thing. It's just going to be positive. So I'm going to switch to the right wing. And I'm going to put in 0.025. And I'm going to get the same thing, just positive. So my T-score is 2.1314. Now, if we want to check it just like before, just to review, if I want to make sure that I get 95% in the middle when I do a between, I'm going to change this to a between. I'm going to make this a negative 2.13145 on this side. And then here I'm going to put in positive 2.13145. And what do you know? There's 95% in the middle. That's the shaded area. So we know we have the right cutoff points. So our t-score is 2.13145. Let's round it to two places to be consistent because that's what we've been doing. So we'll round it to 2.13. So I'm going to write all of this down, what we found from GeoGebra. We got that our mean for the sample was 118.4375. We got that our sample standard deviation, the S, was 5.6565. And we got that our t-score for a 95% confidence with a degree of freedom of 15, we got that that was 2.13. Now for the confidence interval, we got 115.42. That's our lower limit. And then our upper limit was 121.45. So there's our confidence interval. And we would say we are 95% confident that the true population mean lies between 115.42 pounds and 121.45 pounds of beef. Okay, now for the sake of practicing, let's try to calculate our error. So the error for a t-interval is t critical times the sample standard deviation divided by the square root of the sample size. We said our t critical is 2.13. Our sample standard deviation is 5.6565, and we're going to divide by the square root of our sample size, which is 16. When we do that, we get 3.01208625. Ran out of space. So here's our error. So this is what we need to add and subtract to our point estimate, our x bar, to get our confidence interval. So let's check. If we take 118.4375 and we subtract 3.0128625, that was our error, we get 115.42. That works. Now if I take 118.4375, our point estimate, and add the error to get our upper bound, we're going to add 3.012088625, and we get 121.45 when we round to two places. So this matches what we did by hand and what we did on GeoGebra.